Okay, today we're going to look at this modified Atwood machine. We have a 5 kilogram block on a frictionless surface. There's a string tied to it. It's attached to a 1 kilogram object, and that string runs over a pulley. And we want to figure out the acceleration of the two blocks. Now, since they're tied together by a string, they're going to accelerate at the same rate. So first off, let's consider our old way of doing it. We ignore the mass of the pulley. So what we would do is we would look at the forces acting on each block. So for the 5 kilogram block, there's a gravitational force, there's a normal force, but the important one that we're going to look at is the tension force, which I'm calling T1. Now, since the tension force is the only horizontal force acting on that 5 kilogram block, it is the net force in the horizontal direction. So it equals the mass of that block times the acceleration. Now for the 1 kilogram block, we've got a gravitational force down of 9.8 newtons. Now we know that this is going to accelerate in this direction, so this tension force, which I'm calling T2, is going to be smaller than 9.8 newtons. And it's smaller by amount equal to ma. So I'm going to take the mass of that and multiply it by the acceleration. All right. Now, key thing here, we know that T1 equals T2. So 5a equals 9.8 minus 1a. So 6a equals 9.8. All right, so some quick math tells us that the acceleration is 1.63 meters per second squared. All right, and that's ignoring the pulley. Now, we're going to think about what's going to happen when we add the pulley in. So now, some of the gravitational potential energy stored in this block is going to make the pulley spin. We've been ignoring that, which means once we add that in, the acceleration of the two blocks should be less than 1.63 meters per second squared. And here's how we're going to do it. We're going to consider the net torque acting on the pulley, and we're going to set that equal to I alpha. Now, what's causing the torque on the pulley is T1 and T2. Now, because the pulley has mass and it takes energy to get the pulley moving, in reality, T1 and T2 are not the same size. This is an idealized situation when we ignore the mass of the pulley. All right, so now the torque. Is the force times the distance from the center. All right. Now, in this situation, the force that's acting on the pulley is the tension. So we have two torques, one caused by T2 and one caused by T1. So when I look at the net torque, I'm going to take T1 times R, I'm going to add to it T2 times R. That will give me my net torque. All right, this is going to equal I alpha. Now, since we're talking about a pulley, I'm going to call it a solid disk. The torque is mr, the moment of inertia is mr squared. And I'm going to write mr squared like this. Mr times r. It's the same thing. Now, times alpha. And I think you can see why I did that. R times alpha is acceleration. And also, this term has an R, this term has an R, this term has an R. They go away, okay? So, T1 plus T2 equals MA. All right, now, one of these tensions has to be positive, one of them has to be negative, all right? For this problem, I'm going to call this the positive direction. All right, now, I drew in these original arrows for the tensions pulling on the block. T2 is pulling the pulley this way. T1 is pulling the pulley that way. I'm going to call this positive and this negative. Okay, so T1 is negative 5A. T2 is 9.8 minus A. And this equals the mass. I shouldn't be so vague with my mass. This is the mass of the pulley, MP, mass of the pulley. So this equals 0.5 kilograms times the acceleration. All right, so we've got one unknown. Let's simplify this and solve for that one unknown. So on the left-hand side, I've got 9.8 minus 6a. This equals 0.5a. Add 6a to both sides. 9.8 equals 6.5a. Divide both sides by 6.5. And we're going to get a smaller number than we got over here because we only divided by 6. And I already did this out, so I know this comes out to be 1.57 meters per second squared.